Welcome everyone to a podcast on descriptive statistics. My name is Michael Carsey. Let's begin. So the outline of this podcast will be to define the descriptive statistics used in clinical practice as well as the USMLE boards. Some of the objectives for this podcast will be to identify the correct scale for a variable, select the correct measure of central tendency, select the correct measure of dispersion, which we'll discuss, differentiate between the standard deviation and standard error over mean, something that's commonly confusing topic in the literature, as well as discriminate between important statistical graphs, which could be quite useful for studying clinical papers. So within statistics, one of the disciplines is biostatistics, which is the analysis of biological data. And biostatistics can be divided into descriptive statistics and inferential statistics. We'll be discussing descriptive statistics in this podcast, and it has to do with summarization of data using discrete values such as mean, median, mode, and standard deviation, which we'll discuss, versus inferential statistics, which is the process of drawing conclusions using probability, such as using t-tests, correlations, and risk ratio, and this will be discussed in subsequent podcasts. So first we should discuss what is a variable. Well, a variable is a characteristic of a subject that can be measured. It can be broadly broken up into categorical or qualitative variables and continuous or quantitative variables. Now, really one type of categorical variable is important in statistics, and that is the nominal variable. And these are variables that are mutually exclusive, non-overlapping categories, and one where an order is not meaningful. And examples of this can include gender, race, and eye color. Now, higher order of variables, that of the ordinal variable. These are mutually exclusive, non-overlapping categories that can be ranked, such as cancer staging, patient status, etc. And higher than that is that of the interval variable. These are data that can be numerically ranked with unlimited numbers of equally spaced categories, but without a meaningful 0 point. So things like standardized test scores or measures that are oftentimes arbitrarily created. The highest type of variable is that of the ratio variable. This is ranked data where the difference between groups is meaningful and has a true point. And a lot of clinical variables fall into this category. Things such as height, weight, time, cholesterol levels, you name it. These are important concepts to keep in mind because different types of statistical tests will be attributed to the type of variable that is being studied. And many times in clinical papers, you'll find that the incorrect statistical test is often used simply because of lack of understanding of the nature of the variable that is being studied. And oftentimes, a type of board question can be one where a student is presented with a type of data and then asked what kind of way could be used to measure that. And an understanding in how data can be presented for categorical versus continuous will help with the understanding of what kind of statistical test could be properly used. And this is a common chart found in statistical textbooks, not one that needs to be memorized, but one that over time and over the course of a statistical class, a student would definitely be able to understand. But the one point I definitely want to make from this is that if you could find the type of variables you're interested in, shown in the top in red, the category of the variable that we've just discussed can help to differentiate what kind of statistical test you'd use to describe that data. And if you see below in the blue, these are once you get groups of data and you can categorize them by the different level of variable that they are, you can simply look up in this table and find what kind of statistical test you would use to study those kinds of data. And for most part, because we're dealing with ratio data, because this is clinical, these are clinical variables, you'll find that the t-test comes up time and time again as probably one of the most commonly used tests in statistics. So why use statistics? Well, one of the key points about clinical data is variation. Now shown here in red is what we would like to describe as the true clinical variable. Some variable shown on an x and y coordinate axis changing in two directions. Now the true clinical variable is the true underlying biological variable. However, this variable in real time shows variation. There is biological variation as well as systemic variation, such as the time of day that you measure it, etc. And even on top of that is the measurement variation. Clinical variables are notoriously difficult to measure and can vary from time to day, the group that you're studying, you name it. And one of the common problems is trying to get back to this true clinical variable. So as you can see here, the x shown in blue is what we measured, and what we're trying to figure out is the 0 or the O in red, and that's the difficult part in trying to measure. The variability in the data is what makes it difficult to properly and precisely often measure true clinical variables, and so we use statistics to try to get an understanding of how close we are to that true value that we oftentimes don't know. So this brings up the concepts of accuracy versus precision. So accuracy, shown here in the top, is where you have measured data and data fall very close together. You have somehow in a systematic way found ways of measuring data, and your method of measuring them is consistent and reproducible. Now, inaccurate data can be things that are accurate in measuring the data, but they just somehow fall off the mark. They don't seem to be able to measure the proper point, which is in this case the bullseye in yellow. They seem to be they can be grouped close together as well, or scattered, but they seem not to be able to measure that true yellow, which is that true clinical variable that we're trying to get back at. Now, on the other hand, you have measurements, these concepts of precision. Now, precision is the ability of data to be grouped closely together, and that is shown here on the left side by how close these marks fall together. Now, the best data is one that is both accurate and precisely measured, where these reproducible marks fall on the bullseye, and imprecise data kind of gets scattered. And imprecise data can be accurate as it falls on the bullseye but is scattered, or it can be both imprecise and inaccurate, shown in the lower right, where data are both scattered and off from the bullseye. These can be studied in statistics using descriptive statistics, where accurate data can be measured by measures of central tendency, such as mean, median, mode, and skewness, or precision can be described by measures of dispersion, such as range, variance, standard deviation, percentiles, quartiles, kurtosis, and standard error, which we'll discuss further. Now, a quick type of question that you can see on the boards, and this is very common. This is a question that I've seen in practice on the boards, and it reads, a new assay measures serum cholesterol for a given lab value where the true cholesterol is known to be 140 milligrams per deciliter based on the gold standard. A sample is performed 4 times, resulting in the values 80, 85, 88, and 90 milligrams per deciliter. This new assay is A, not accurate, B, not reproducible, C, not precise, D, not specific, not sensitive, or E, not specific. And the answer is A, not accurate. So this question shows that measured values are off from the true sample value and therefore not accurate. However, the measured values were both close, they're close together, therefore they were precise and reproducible. Hence, these two words could be almost used synonymously. The concepts of sensitivity and specificity refer to how effectively a test measures a disease, and it really would not be indicated in this case where true clinical value is not given. So these are really irrelevant answer choices. Another question: a clinical test measures serum partial thromboplastin time and a sample is performed 4 times, resulting in the values 24, 30, 60, and 65. The test is A, not accurate, B, not valid, C, not precise, D, not sensitive, or E, not specific. And the answer here is C, not precise. Precision is the correct answer in this case, as the data are not consistently measured, and accuracy refers to how close to the true clinical value these data measure, and it's irrelevant in this case. And validity is this vague statistical term, very similar to accuracy, but it refers to how effectively a test measures what it's supposed to measure. This is kind of a vague term, so it can be subject to interpretation. Since no true clinical value is being discussed in this case, this is again an irrelevant choice. And again, sensitivity and specificity refer to how effectively a test measures a disease, and these are also not relevant answers in this question. So let's start discussing what the measures of central tendency and the measures of dispersion are. Now, these are single numbers that convey information about accuracy and precision, like we've mentioned. Okay, measures of central tendency, therefore accuracy, are mean, median, mode, and skewness commonly used. There are other values that can be described, but these are the more common ones used. Measures of dispersion, which therefore measure precision, are range, variance, standard deviation, percentiles and quartiles, and standard errors. Again, there are additional types of measures that are used, but these are the most common ones which we'll discuss. Measures of central tendency. So let's start talking about the arithmetic mean. This is also known as the average. It's calculated by adding all the values of the population and then dividing by the number of values that are added. One of the key concepts to keep in mind with the mean is that it can be wildly skewed by extreme numbers, therefore otherwise known as outliers, especially when the number of observations is small. Now shown here is mathematical notation. It's definitely nothing to get scared from. This is just an easier way to describe what the process of calculating a mean is. So it shows here x bar on the left is equal to the sum of x divided by n. Okay, this x bar refers to the mean of the observations. Sigma, or sum of x, is the sum of all the observations, and divided by n, commonly a variable used to refer to the number of variables in this operation. And very, very quickly, a discussion on how the summation works. You can see sigma with the n on top, which discusses the number of terms that you're going to be adding up, and the number on the bottom of the sigma, where it says I equals 1, that equals which term you start with. And then the term on the right side, called the typical element, those are basically some notation indicating which terms you're adding up. So with the arrow indicating what's commonly used as as the sum of a set of numbers, you can see that you start with x1 and then add up all the way to x10. Therefore, I equals 1 and the top number equals 10. Just a very common, simple way of using summation in statistics. So an example of a mean calculation, you have a list of subject ages, you add them all up, divide them by the total number, and you get your answer. Now median, this is a value that divides a sequential set into two equal parts. If the number of values is odd, the median will be the middle value. However, if the number of values is even, the median is the mean of the two middle values. Now the remarkable capability of the median is that it's insensitive to outliers in measuring central tendency. Mean and median should also be kept in mind are symmetric or are the same number in symmetric distributions. So an example of how to calculate the mean, you have a set of numbers organized sequentially. You count the number of numbers. If it's an odd number, you can go back to the middle number and find what the median is. However, in the set below, you have an even set of numbers, and therefore you have to take the mean of the two middle numbers and get your answer. And mode, this is a number that describes the number that is most frequently found. And one thing that can be kept in mind is that you can have one mode or a unimodal distribution, multiple modes, bimodal, trimodal, or no modes in a set of numbers. And the way this is calculated is you basically just look at what the most common numbers are that pop up in a set of numbers. The first example, the mode is 57, which appears twice. In the second example, you have a bimodal distribution where the number 20 appears 3 times and 27 appears 3 times. Whereas in this third example, you have no mode because no number comes out singularly as the most common number. The concept of skewness is something important to keep in mind, where both mean, median, and mode are importantly discussed. If you have a normal distribution, shown here, this Gaussian distribution, this is basically a normal distribution of individual values. These values can be skewed to the right or to the left. If they're skewed, this is often something called a positive skew or a right skew, and it's often described as where the tail is. And here, since the tail of this distribution is towards the right, we call it a right skew. The green graph, shown at the very bottom, is a negative skew or a left skew, where the tail is shown towards the left. Now, important concept of skewness are where the mean, median, and mode fall on the graph. In a normal distribution shown in blue, mean, median, and mode are the same number found at the middle of the distribution. However, if you have a positive skew, the mode will stick with the hump of the graph, and the median and the mean follow suit next to it. This is a case where the mode, median, and mean are different numbers. And it's important to keep in mind because when you start to describe clinical data and you don't have a normal distribution, then maybe the mean might not be the most effective measure of that distribution. Similarly, if you have a negative or left skewed distribution, mean, median, and mode follow in suit. Now, one of the easiest ways to remember which direction the mean, median, and mode are going is to just think of the left skewed distribution where the tail is to the left, and then note that mean, median, and mode are in alphabetical order. The mode is obviously always going to be the top number, so it's going to be the hump of the graph, and the mean, median, and mode will follow suit. Now, question, very similar to what you might see on the boards, reads as follows. The following are survival times in months recorded for 6 patients with terminal metastatic cancer after chemotherapy: 1.2, 2.4, 2.4, 3.5, 3.6, and 4.7. If the observed value of 4.7 months was mistakenly recorded as 47 months, what would be the effect on statistics for this study? Would it be A, an increase in the median, B, an increase in the mode, C, an increase in the mean, D, an increase in both the median and the mean, or E, an increase in the median, mode, and mean? The answer is C, an increase in the mean. And this is why. If you take your numbers and you add them all together and divide by the number of samples, you get a mean of 2.967. The median, again, is the two middle numbers, which is calculated for you, and the mode is the most common number shown. However, in the second set of numbers, with 47 as our outlier, mean equals 10.001, or almost 3 to 4 times larger than the mean from the first set of numbers. Median is calculated and is unchanged, and mode is calculated and unchanged. And one of the key concepts to take away from this type of problem is that means are very often skewed by outliers, and therefore something that should be kept in mind when trying to describe a set of numbers, especially when they're small or there are outliers included. Here's a fourth question. The number of data represent length of hospitalization in days for 6 patients post-operatively: 3, 3, 5, 6, 7, and 30. The best measure of central tendency is A, mean, B, median, C, mode, D, range, or E, standard deviation. And the answer here is actually B, median. The median would be the least skewed by an outlier in this set, namely the post-operative day of 30. And mean would be commonly recorded as the measure of central tendency should this kind of data be found in literature, but oftentimes this is not an accurate assessment of this data, especially in this case when we're dealing with a very small set of numbers and a significant outlier. The mode and the range would not be useful as they do not explain that outlier very well, and standard deviation is a measure of dispersion and not central tendency, which we will discuss subsequently. So the measures of dispersion that we'll discuss are the range, variance, standard deviation, percentiles and quartiles, and the standard error. The range is the difference between the largest and the smallest value in a set of observations. Sometimes the range is reported as the actual lowest and highest observations. So as you can see below in the set of numbers, take the highest subtracted by the lowest and you get your range. Variance is a number that is used to describe the scatter of the values about their mean. And it's taken as follows. You basically sum the difference of an individual value from the total mean of the group of values, shown as x bar. You in one parentheses, square those, add all those numbers together, and divide by n minus 1. Now, one of the problems that you fall into when you're dealing with variance is that if you have negative numbers in your set of numbers, your variance will often come out a little bit weird. It will come out sometimes as 0, even though you have a widely skewed set of numbers, and it doesn't offer very good description of what your data are actually doing. Therefore, this concept of, and here's an example of how you calculate variance. Take the numbers, take the mean of them together, take the numbers individually and subtract them from the mean, square them, add them together, and divide by the total set of numbers, and you get your variance. However, if we had negative numbers in this set, we would have a difficulty in describing what the variance would be, and so the concept of standard deviation is used. And this is it's basically the variance, but you take the square root. Now, the way that you do this is you, again, take each of your values, subtract them each by the mean of the set of values, square them, sum them all together, divide by n minus 1, and take the square root of everything. The reason that we divide by n minus 1 and not n is a kind of arbitrary / complicated mathematical statistical reason having to do with when you square numbers and divide them by the number of observations and then take the square root of those. And it's something that requires a lot more study to fully understand. But it's not important for the understanding of this concept of standard deviation. And so here's an example of how to calculate that. You have your subject ages and their mean. Take each value, subtract from the mean, square root, take the square of them, add all the numbers together, divide by the number of observations minus 1, and then take the square root of the whole thing, and you get your end product, 9.486. Now the last, one of the second to last concepts in measures of dispersion are percentiles and quartiles. Now percentiles is the value where p% of observations will be less. So therefore, understanding of this is that at the 25th percentile, 25% of the values will be lower and 75% will be higher. The 50th percentile should be kept in mind as the same thing as the median. Oftentimes, the percentiles are described as quartiles. So the 25th percentile is the first quartile, 50th percentile is the second quartile, 70th percentile is the third quartile, etc. You can use whatever percentile you want and divide them up as you see fit. Here's how you can calculate quartiles. For the first quartile, you basically multiply 1/4 by n plus 1 of your set, and therefore that number which you get is the first quartile number. And then you go forth 1/2 times n plus 1 for the second quartile, and then 3/4 times n plus 1 for the third quartile. And in a set of observations, you can see you add up the total number, 11 plus 1, divide by 4, and you get the third observation, and you look it up and it's 43, and so on and so forth. Now, a very easy way of looking up these numbers, if you have a small set, is shown at the bottom. If you take all the numbers and you write them out sequentially, again, as we said earlier, the second quartile is the median, so you can look up what that number is, 57, and the first quartile and the third quartile are essentially medians of that smaller set of numbers. So from 36 to 57, if you look up what the median of those sets of numbers are, it would be 43, and if you looked up the median for numbers from the second 57 all the way to 66, the median for that would be 46. So essentially you have 3 medians equaling your 3 quartile numbers. And a common way that quartiles and percentiles are described is something called the Box-whisker plot. It's a very effective way of showing how your data are skewed around their distribution. Now, shown here, the box indicates the quartiles and the median. The M represents the median or the second quartile. The Q1 is the first quartile, and the Q3 is the third quartile. And what the tails are the lines where they basically extend out to the range of your numbers. So the leftmost tail, or the leftmost whisker, is kind of the lowest number in your range of numbers, and the rightmost whisker is the highest number in your range of numbers. And oftentimes we can describe outliers also on the Box-whisker plot, and we use 2 common standard ways of describing outliers. Outliers that are 1.5 times the interquartile range are described as outliers, and they are oftentimes represented outside of the whiskers by some sort of number or symbol. And then numbers that are 3 times the interquartile range are described as far outliers, and also described on the plot by some sort of symbol or number. And so this brings us to a point on describing the difference between standard deviation and standard error of the mean. These are common values that are described in literature and seldomly really understood. So I'd like to talk a little bit about what the difference between these 2 numbers are. The standard deviation is often referred to as sigma, shown here, and standard error is sigma divided by the square root of n. Standard deviation describes variables of a set of individual observations, while standard error describes variability in the true population mean. So one of the ways of thinking about standard deviation is that it's useful for describing how the skewedness of a set of numbers really is, while standard error is really addressing a different point. And remember back when we talked about how biological data is clinically hard to measure and extremely variable. Well, standard error is used as a way of trying to see how close do your measurements fall to that true clinical value that we're trying to measure. And again, as you see, we're dividing by the square root of the number of observations in our set. That's important to know because what we're trying to say with this number is that as you add more data to your set of observations, you are reducing your error, and therefore you are more precisely and able to describe what that true clinical value is that you're trying to get back to. So some examples of standard deviation versus standard error. Standard deviation, say if you're studying hospital department infection rate variability, you could assess differences in infection control protocols. Whereas if you're using standard error to describe the same type of study, what you're trying to do is assess the true community infection rate, because then you're trying to get back to what the true clinical variable is. Whereas standard deviation is just trying to describe how variable are the data that you're measuring. Another concept is precision of a laboratory machine in measuring a clinical value. So from sample to sample, standard deviation could be extremely useful in showing you how effective your machine is in measuring a particular value. Whereas if you're using standard error, you are attempting to use that laboratory piece of equipment to study the true clinical value, like the true cholesterol value or the true, serum lactate dehydrogenase value. That's really what you're trying to get back at. Now, standard deviation is unchanged by sample size because it simply just describes your set of observations, whereas standard error decreases as the sample size increases. It's trying to get back to that true clinical value. And standard deviation you can study in Excel. If you have a set of data, you can easily calculate this on your own. It has a function built into Excel. And standard error does not have the standard function built in, but you can basically write your own, shown here, standard deviation divided by square root of the count or number of observations. You can easily use these two numbers in your own research projects describing your own data, and now hopefully you might have a little bit more understanding of when to use these different numbers. So one of the things I wanted to talk about are charts and figures in statistics. Now, this is a kind of funny grouping of different types of charts used in research. And we're not going to discuss all of them, but we will try to discuss kind of the most important ones used in statistical research or clinical data presentation. The first one is the histogram, which is basically a chart used by responsible analysts who understand the power of segmentation and the sadness that comes from aggregated data. And it has to do with basically describing that distribution that we've seen earlier. And it's a great way of basically taking variables by different increments and adding up what the frequency of variables within those increments add up to be. It's very similar to the bar chart shown here, which is a safe choice, but make sure you read Stephen Few before you show the chart to your boss. It will increase your probability of getting a raise. Now, bar charts, we can arbitrarily set what the x-axis is or what we want to measure. So unlike the histogram, we're not using discrete values of equal length and then describing the frequency. Instead, we're setting up different categories and then measuring the frequency of values within those categories. And the last chart on this page that's commonly used in statistics is the line chart, and it's used to show trends, especially upward. For downward trends, people tend to use more obscure data, like the waterfall chart seen below. Oftentimes, if you don't like data that doesn't match your hypothesis, you can obscure it, and there's lots of ways of doing that. And the line chart is great for showing trends. Other charts are shown here, the most important of which is the scatter plot. It's very useful to find outliers on this plot, just like the people that commonly create them, human beings that finish their PhD in math by the age of 16. Basically here you plot data on the x and y axis, and it's useful for finding individual data points that fall far from that axis. And those outliers can be due to poor measurement, or they could present very interesting clinical scenarios that require further study. And the last figure on this page is that of the box plot, which we've already discussed. And this one's for the pros. If you use it successfully, you get a seat in heaven between Ronald Fisher and Johann Carl Friedrich Gauss. So again, as we showed the box plot, you can have multiple box plots measuring different things, and they're great for looking at your data very quickly, seeing how it's spread out, where the median within that data is, and comparing it to other sets of data. And all these types of figures can be commonly used in statistics, in clinical presentation of clinical data, and they can also be easily created using various common statistical software that are available. Now, this brings us to a couple points I wanted to make about figures, and one point is the misleading use of figures often found in the clinical literature. So this is a study in 2003, and it looked at 3,185 total advertisements in 10 very prestigious U.S. medical journals, shown here such as American Journal of Psychiatry, Emergency Medicine, Internal Medicine, Surgery, you have New England Journal of Medicine, etc. And one of the things that came from this analysis was that by studying these pharmaceutical advertisements, These researchers found that extraneous decorations were found in 66% of the charts that were presented, making it difficult to analyze what data they're presenting. Redundancies were found in 46% of the data, and numerical distortions, specifically prohibited by FDA regulations, were surprisingly found in 36% of graphs. So one should keep in mind when looking at pharmaceutical advertisements in medical journals or anywhere else that the graphs are not always clinically valid, that they might be used as advertisement pieces, and one should be using their own clinical judgment in figuring out whether the data being presented is accurate or not. Now, just to leave the pharmaceutical companies not totally without blame, this is a study looking at researchers, and it was from a group in 2006, and found it studied 62 randomized clinical trials published in the British Journal of Medicine, and you can see the difference between the figures that were submitted to the journal and how they were finally published. These researchers looked at how the figures were presented, whether the publishers made any changes to the figures, and whether those changes helped to improve the readability and accuracy of the figures that were being provided. One can see here that the kinds of graphs that we just discussed, bar graphs, univariate displays, box-whisker plots, histograms, these are the most common types of graphs used in clinical literature. You do not need sophisticated graphs to present biological clinical data. You commonly will be able to get by with just those simple ones we've just mentioned. But you can see here the difference in figures really didn't change from that of the submitted and published version, and this is the reason why. Numerical distortion was found in 6% of submitted graphs and 3% of the final published graphs. Internal redundancy of the data was found in 8% and 5% respectively, and this chart junk, which is this clinical or this kind of term that the researchers used, which they defined in their study, was found in 6 and subsequently 10% of graphs. Then the one thing to keep in mind is that few graphs really improved from the time of submission to the time of publication, meaning that the peer review process, as studied in this particular study, was not that effective in improving the quality of the data that was presented. And instead, the quality seemed to lie on the researchers that were presenting the data. So that should be something that could be kept in mind, is that whenever you're reading clinical literature, to use your own judgment in figuring out whether that data is valid or not, and not just believing what you read simply because it's been peer-reviewed or presented in a prestigious journal. And here are some tips on how to create really good figures from a study published in 2004. The first thing is, if you're trying to describe discrete points, use the bar graph or the histogram, which we were talking about. Do not use a line graph. The reason why is because the line graph makes it look like these data points are somehow linked together and there's some sort of trend. That's not what we're trying to present, for example, in this particular case. And if you're not trying to do that, you should stick to the proper type of graph to present that data. Another thing to do is to be very mindful of the axes of the graph. Both the axes and when standard deviation and standard error are presented on the graphs. You should really keep in mind what data are the researchers presenting. And shown on the top, you can see this remarkable trend in the data once you chop the axis at 40. However, you look at the data in reality, once the data spreads from 60 all the way to 0, this trend is much, much less remarkable. And the last point is, if you're creating line graphs or any sort of graph, to always keep in mind that the graph can only represent what it presents. So shown here in A, if you have a group of scattered data, you can't really just extend that line and show that the trend continues outside of your group of data. And if, in fact, the better way of presenting this is to show it in B, where the regression line really terminates at the beginning and the end of the data. Basically being responsible in how you present your data and analyze it. So in conclusion, nominal data are categories, ordinal data are ranked categories, interval data are numerical ranked and equally spaced data without a meaningful zero, ratio data are numerical data with a meaningful zero, and keeping these different scales in mind can help with the selection of a proper statistical test to analyze the data. Biological data and their measurements are inherently variable and give statisticians a job. Data accuracy is described by measures of central tendencies such as mean, median, mode, and skewness, while data precision is described by measures of dispersion such as range, variance, standard deviation, percentiles or quartiles, and standard error. Please try to keep these different terms in mind. They come up time and time again on the boards, in clinical literature, etc. Positive or right-skewed data have tails to the right, where mode, median, and mean are found in order. Negatively or left-skewed data have the tails to the left, where mean, median, and mode are found in order, and this is the alphabetical way that this is organized. Standard deviation describes variability in a set of individual observations, while standard error describes variability in the true population mean. And the most useful way to graph data in statistics include the histogram, the bar chart, the line chart, the scatter plot, and the box plot. These are the most commonly used and easiest to understand. And you should always critically analyze newly presented data and graphs.